In the 12th lecture, we'll be discussing acid-base buffer systems. And the title slide shows you a good example of what a buffer system is. It is a weak acid, and its conjugate base. And when these are in mixture together, what happens is they resist changes to pH quite well. If you add an acid to it, so if you add, in this case we're showing the acid by the H+, it's going to react with the conjugate base in that buffer system and produce some more of the weak acid, right? And remember, weak acids don't dissociate very much, and the concentrations change slightly, but that takes away that H+ from solution, so it's resisting the pH change that you would normally see when you add that H+, that acid. And likewise, when an OH- is added, that's going to react with the weak acid, right? And some of the weak acid can give up protons to that OH-, that base, and then the relative amounts of the weak acid and conjugate base change a bit, but it resists that change in what would be the change in pH, the increasing pH by adding a strong base. Right, so this is chapter 19 material where we'll be starting after finishing chapter 18. And in particular today, the material will come from section 1 and a little bit from section 2. Right, so what is a buffer? An acid-base buffer is a solution that lessens the impact of pH from the addition of an acid or a base. Okay, so that's what buffer means. It's resisting the impact of a pH change from an acid or a base. Right, an acid-base buffer usually consists of the conjugate acid-base pair. That's the most common, easiest way to make a buffer. And both species are present in large enough quantities, okay? And for it to be an effective buffer, usually they're in similar quantities to one another, the weak acid and the conjugate base. Right, so the buffer is going to be a solution of that weak acid and its conjugate base, or a weak base and its conjugate acid. So that's really all a buffer is. And here we see just an example of how a buffer could be used. So if you have a 100 milliliter sample of dilute hydrochloric acid, you adjust it to pH 5 on the left, and then you add 1 ml of a strong acid or 1 ml of a strong base to it, and you see that the pH changes a great deal, right? If we add a strong acid to it, it goes down to 2. If we add a strong base to that, it goes up to 12, right? So that's a big jump, 5 to 12, just by adding 1 milliliter to 100 milliliters. Right. Now if we have a buffered solution, so the buffered solution's at pH 5, you add the same amount of 1 ml strong acid, 1 ml of strong base, now that pH barely changes at all. Okay, so that's a good example of what a buffer system does. And in our bodies, in our bloodstream, and inside our cells, we have buffer systems. So we can resist pH changes like this. And some examples of those, one of the biggest examples in the blood is our bicarbonate. Right, so CO2 that it can be dissolved in your bloodstream as a gas. When it goes into these blood cells, there's an enzyme called carbonic anhydrase that converts it into bicarbonate. And then that bicarbonate can leave outside of the cell through this transporter. Okay, and it exchanges a chloride in, so the net charge difference does not change inside the cell. Okay. So in respiring tissues, you're producing a lot of CO2, so there's more CO2 dissolved. It comes in, it gets converted to bicarbonate, right? Then in the lungs, your bicarbonate can leave your bloodstream, go back into the blood cells, get converted back by the same enzyme, carbonic anhydrase, to CO2, and then it goes out dissolved as a gas, and you can exhale it. So that's one way the body regulates the amount of bicarbonate you have. Okay. And why it's important, if you look over here on this slide, your bicarbonate ion, if you add an acid into your system, into your bloodstream, that's what reacts with that proton and produces carbonic acid. Right? So that's a weak acid, right? So that buffers the change you would have by adding these protons. So this is the major buffering system inside our bodies. A buffer works through the common ion, what's known as the common ion effect. Okay, acetic acid in water dissociates slightly, as we know, it's a weak acid, to produce some acetate anion. Well, if sodium acetate is added, it provides a source of that acetate ion. And the equilibrium is going to shift then to the left, right? And so that acetate ion is what's known as a common ion. It's common to both solutions, both the acid, the weak acid, and its conjugate base. Okay, the addition of that acetate ion reduces the percent dissociation of the acid. So if we look at solutions now, they all have the same concentration of 0.1 molar acetic acid. And then if we look at varying amounts of acetate ion added, we can calculate the percent dissociation, right? And remember, we did this in a practice problem a few lectures ago. The percent dissociation is just going to be how much of that weak acid dissociates, which you can calculate through an equilibrium expression with the Ka, and divided by the starting amount of that times 100. Okay, so when you do that for these, right, if you don't have any acetate, you get 1.3% dissociation. If you add 0.05 molar, you get 0.036%. And as you increase this amount, the percent dissociation is decreasing. And shown here is the amount of H3O plus and the pH. There's a big jump here you see when you add none and then you add a little bit, right? You get a pretty big jump there, but as you double this and then add another 0.05 molar, you can see that the change, it gets less and less each time. Right, so if you want to look at the relative amounts of each of these systems in the buffer, right? Well, you can write this buffering system. It's going to be the same equilibrium expression that we've been using for a weak acid. Right? You can write that Ka expression the same way. Right? You can then solve for your hydronium ion concentration, because that's probably what we're going to be most interested in to calculate a pH. And that would be equal to the Ka times the ratio of these buffering components. Ka is a constant, so the solution's really going to depend, the pH of the solution is really going to depend on the ratio of those buffer components. So if the ratio of weak acid to conjugate base increases, your H3O plus is going to increase, and therefore your pH will decrease. If the opposite happens, if that weak acid concentration relative to your conjugate base decreases, your hydronium ion is going to decrease, and then your pH would go up. The buffer components, HA, that's the weak acid, just a generic way to write it, and A minus, your conjugate base, are able to consume small amounts of OH minus and H3O plus by shifting in the equilibrium position. Okay. All added OH minus is going to react with your acid, causing a shift to the right, and all added acid H3O plus is going to react with your conjugate base and shift the equilibrium to the left. The shift in equilibrium position absorbs the change in both the acid or the base added, and the pH therefore changes only slightly. So if we look at this pictorially, here we have our buffering system. You have the weak acid shown here, and then the conjugate base. Okay, and they're in equal molar to each other. There are 4 molecules of weak acid, 4 molecules of base. Right? When we add that weak acid, right, that's going to react with adding the acid is going to react with the conjugate base, right? And that's going to produce some more of that weak base. And so here, that's shown as, if you have one molecule, one hydronium ion molecule, it's going to react with one of those. And now we have 5 of molecules of our weak acid and 3 of our base, right? It's reacting with that conjugate base, changing the concentrations of these slightly, but that buffers the pH change that you would get. And likewise, OH minus would react with our weak acid to form our conjugate base and lessen the effect that OH minus would have if it was free in solution. Okay, let's try a practice problem with this. Calculate the effect of added H3O plus or OH minus on a buffer pH. Okay, so there's 3 parts to this. Okay, first, calculate the pH of a buffer solution consisting of 0.5 molar HClO, which has a Ka value given here, and 0.6 molar NaClO. Okay, so we'll do this one first. So for part A, it's always helpful to write out the chemical equation. Oops. So we have HClO plus H2O goes to ClO minus plus H3O plus. And we're starting with 0.5 molar HClO, no water that we don't consider, and we have 0.6 molar of our conjugate base. Okay. So at equilibrium, that will be minus X. H2O, don't consider. This will be plus X. So here we have 0.5 minus X. And this would be 0.6 plus X. Okay, so for this equation, or for this example, Ka is much less than 1, right? It was 2.9 times 10 to the minus 8. So we can assume that our weak acid is about, what we started with, 0.5. You can also assume that that conjugate base you started with is going to be just about 0.6. Okay, so you're assuming that there's no real changes here because the amount that these dissociate is very small. So now what you want to do is solve for X, and X is the hydronium ion concentration. Right, so X equals H3O plus. All right, and if you write your expression for Ka, which we should be all familiar with now, and rearrange that to solve for H3O plus, it would be Ka times HClO divided by ClO minus. Right, and we know that equals 2.9 times 10 to the minus 8 for the Ka. And the concentrations of your weak acid was 0.5 and 0.6 for your conjugate base. So X is going to be equal to 2.4 times 10 to the minus 8 molar. And to calculate the pH, right, we're just going to take the negative log of that, negative log of hydronium ion concentration, which was 2.4 times 10 to the minus 8, which would be 7.62. Okay, for part B, we need to calculate the pH after adding 0.02 moles of solid NaOH to 1 liter of the buffer solution in part A. Okay, so now part B, we're making this more complicated. So when you do a problem like this, you have two reactions that you have to consider. So the first, you have to consider what it is when you're adding your acid or your base. So for adding base, that's going to react with our weak acid. And so that's going to convert our weak acid into that conjugate base. But the OH minus that was added will be converted to water to neutralize it. And so we started with 0.5 molar of HClO, and we're adding 0.02 moles per liter of our OH minus. And so what is that going to produce? And we also have to consider our weak base. We started with 0.06 moles of that. Well, how's this going to change at equilibrium? Well, we're going to use up all of the base that was added there. We're going to use that up on the reactant side, and that will be added to the product side that conjugate base will form. So now our new concentrations would be 0.048 molar weak acid. We don't have any OH left because it all got reacted with, and our weak base is 0.62. Okay, so that's how it would change by adding that base. Now we can go back to our original equilibrium. And plug in these new values. So now we have a new initial value. So our new initial value for the weak acid is 0.48. New initial value for the conjugate base is 0.62. So how do they change? Right, they minus x plus x plus x. But we're assuming this would be 0.48 minus x, and this would be 0.62 plus x. Okay, but we're assuming our x's are very small compared to what our starting concentration is, so these basically stay the same. That's our simplifying assumption. Right, so now we can solve for x again. X is just going to be Ka times acid concentration over base concentration. So that's 2.9 times 10 to the minus 8 times the fraction of 0.48 divided by 0.62. And that equals 2.2 times 10 to the minus 8. And if we calculate the pH from that, pH equals negative log of 2.2 times 10 to the minus 8. That is 7.65. Right, so you see that the pH, after we added that strong base, the pH really didn't change much. It went from 7.62 to 7.65. Okay. Final part, after adding 30 milliliters of 1.5 molar HCl to half a liter of the buffer solution in part A. Okay. In part B, assume that the addition of NaOH causes a negligible volume change. This question, part C, gets harder because we don't necessarily, we're not necessarily assuming that, so we have to take into account the volume that we're adding from the acid. So this is an example of how things can get more complicated. Okay, so let's first consider our volume. So we're going to have a new volume. We started with 500 milliliters, 0.5 liters, and we're adding 30 milliliters. So our new volume is going to be 0.53 liters. Right, so now we can calculate our new starting amounts. So starting amount of our acid is just going to be M1V1 over V2. So we had 0.5 molar times 0.5 liters divided by 0.53 liters, our final volume, which would be 0.47 molar. H3O plus concentration we have 1.5 molar times 0.03 liters that we're adding. The final concentration would be 0.53 liters, so that concentration is 0.085. So that'd be the final H3O plus concentration when we add it in to the bulk mixture. And then finally, ClO minus concentration. We start with 0.6 molar with 0.5 liters when that goes to final volume of 0.3 liters after we add our acid, HCl. We get 0.57 molar. Okay. So now we can consider our addition of our HCl, or acid. So when our acid is added, it's going to react with our conjugate base. So if we write this, it's maybe a little bit confusing to write, but it's actually going to go in this direction. If we have our ClO minus plus HCl. Well, what's going to happen? And I suppose this isn't H2O, it's just Cl minus. And so we're starting with 0.47 molar of our acid, 0.57 molar of our base, and we're adding an amount of 0.085 molar of our HCl, which will react with our conjugate base to form more of our weak acid. Okay, so these are both going to lose 0.085. This will be increasing by 0.085. So those values now are 0.56, 0.48, and 0. Okay, and so you could probably see where this is going, but I'll just write it out again, the long version. Okay, our reaction or equilibria between the two weak acid conjugate base is shown here. Okay. We have new starting amounts or initial amounts, 0.56, 0.48, and 0. All right, then we just would do minus x plus x plus x. But again, we're just assuming that these don't change, or at least they don't change very much. Right, so we're going to be calculating x again based on Ka times the ratio of our acid over base. So that's 2.9 times 10 to the minus 8 times the ratio of 0.56 divided by 0.48, which equals 3.48 times 10 to the minus 8. And if you take the negative log of that, we get 7.47. Okay, so we're adding acid. The pH is going to go down, but it doesn't go down by very much. So here's a summary slide showing the effect of an added strong acid or strong base on a buffering system. Right, just if you add acid, right, that acid's going to react with the conjugate base to neutralize itself, and you've produced more of your weak acid. So the concentration of your weak acid increases, your conjugate base decreases in that buffer system. So then your pH is going to go be less, lower. And the opposite happens when you add OH. It reacts with your weak acid, so that concentration decreases. Concentration of your conjugate base increases, and your pH will increase when that ratio decreases. So that whole problem, when we were solving that, we were kind of dancing around what's known as the Henderson-Hasselbalch equation. Okay, so you have if you have this weak acid conjugate base buffering system, you write that Ka expression shown here. You solve it for H3O plus, which we've done, right? That's Ka times your HA over A minus. Okay. If you take the log of that, we know that the log minus log of H3O plus is pH, right? So you can take the negative log of both sides, and this is what you'd get. Negative log of H3O plus is the pH, you can take the negative log of Ka, and that's the pKa, and then you take the negative log of acid over base, and that's where this term comes in. But now it's a little confusing. Now we have a positive, and the log is of the ratio of base over acid. Okay, so that's very important. It's, if you use the plus sign here, plus log of base over acid. I think you could use a negative log of acid over base still, but the Henderson-Hasselbalch equation tends to be written this way. So now our ratio is going to be log of base over acid. So in a sense, we're not going to calculate our H3O plus. You don't have to calculate that concentration and then plug it in to find your pH. You can just sort of do it all at the same time by using this equation. Okay. The term buffer capacity measures the strength of the buffer. That's its ability to maintain the pH following the addition of acids or bases. Okay, the greater the concentration of the buffering components, the greater the buffer's ability is going to be to resist pH changes. The closer the component concentrations are to each other, the greater the buffering capacity will be. Okay. So this graph shows the final pH for 4 different buffer solutions. Okay, you have a 1 molar, 0.3 molar, 0.1 molar, and 0.03 molar buffer solutions. And you add the same amount of strong base added, and how much the pH is increasing is shown here. So you're initially starting at 4.74, and you see that the one that has the highest concentration of buffering components changes the least, which shouldn't be surprising. Because if you start with a larger concentration, you're going to have more room for some of that buffer component to be absorbed or converted from reacting with that strong base or strong acid. The other term that's important in buffers is buffer range, and that is the pH range in which the buffer is effective. The buffer range is related to the ratio of buffer component concentrations. Okay, so the closer the weak acid is to conjugate base concentration, the closer those are to each other, thus the ratio being 1, the more effective the buffer would be. Right? If the concentration of one component is more than 10 times the concentration of the other, the buffer action for that is going to be poor. Okay, since log of 10 is 1, that means buffers have a usable range within plus or minus 1 pH unit of the pKa of the acid component. So in the Henderson-Hasselbalch equation, you have the pH is equal to the pKa plus log of that ratio, base over acid. If your ratio of base over acid is any bigger than a factor of 10, right, log would be 1. So that gives you where that range is, plus or minus 1 pH unit from the pKa value. So let's try a sort of a graphical problem here. You have molecular scenes here, 4 molecular scenes, and they represent different concentrations of your weak acid conjugate base buffer systems. Which buffer has the highest pH? Which buffer has the greatest capacity? Should we add a small amount of concentrated strong acid or strong base to convert sample 1 to sample 2, assuming no volume changes? Okay, so we have our pictures up here to remind ourselves. Okay, also important, I think, is to write our reaction that's occurring. So we have our generic weak acid, and it's in equilibrium with the conjugate base. Okay. So for each of these scenes, we want to find our acid-base ratio. So I'll just write them for for all 4 of those scenes. Okay, so when we look at the first scene, we have 3 acids divided by 3 bases, so that's 1. For 2, we have 1, 2, 3, 4 acids over 2 bases, so that would be 2. 3, we have 1, 2, 3, 4 over 4. So that's ratio is 1. And then finally we have 2 over 4, which would be 1/2. We can convert this into ratio of base over acid, just because this will be easier to plug into the Henderson-Hasselbalch equation. Right, when we do that, that's still going to be 1. 2 now will be 1/2. That 3 will be 1, and then scene 4 would be 2. Okay, so we've converted those ratios to base over acid. Okay, and that's again because we're going to use the Henderson-Hasselbalch, which is pH equals pKa plus log of your base over acid. Okay. So we can plug all those in to find the pH if we had the pKa, but in this case we are not given that. When we can do part of this, right, we can do like a log of our base over acid. So a log of 1 is going to be 0. Log of 1/2 would be minus 0.3. We have log of 1 again of 0 for scene 3, and then the log of 2 is going to be a positive 0.3. Okay, so that's, in a sense, where the pH would be relative to the pKa in these systems. So question A, which one has the highest pH? Okay, so we know that scene 1 and 3, the pH would equal the pKa. Scene 2, the pH would be negative 0.3 lower than the pKa. Scene 4 is going to be 0.03 higher than the pKa. So scene 4 has the highest pKa. Excuse me, highest pH. And you can think of that too. It has the highest ratio of its base to its acid, so its pH would increase. Okay, which has the greatest capacity? Well, remember, capacity is based on concentration. So the highest concentrations were in scene 3. We had 4 over 4 instead of 3 over 3 that's in scene 1. Okay, so that right there would be the highest capacity. Okay. And then finally, question C was asking amount of acid to convert 1 to 2. So if we have, if we look at scene 1, we have 3 over 3 acid over base, and we want to convert that into the ratio of 2. So we'd have to add, in this case, you'd have to add 3 more molecules of HA to get that same ratio. Okay. So how do we prepare a buffer? Well, it's important to choose, the right components. So you do that by looking at the pKa of the weak acid. And that should be close to the desired pH you want your buffer system to be at. So in biochemistry, that's typically when you make buffers, You make a lot of buffers in biochemistry. So you generally look at your system that you're trying to study, like if you're trying to study a protein and you want to find out what pH range it's most active at, then you set your buffer for that pH. You want to look at your buffer components and make sure your pKa is very close to that value. Okay. Then you would need to calculate the ratio of the buffer components concentrations to give you a specific pH that you want based on the pKa and those ratios, all based on the Henderson-Hasselbalch equation. Okay. So you determine the buffer concentration, calculate their volumes of the stock solutions or the masses of the components, and mix it all together. So let's try a practice question making a buffer. Okay, if an environmental chemist wants to have a carbonate buffer at pH 10 to study effects of acid rain on limestone-rich soils, how many grams of sodium carbonate must she add to 1.5 liters of freshly prepared 0.2 molar sodium bicarbonate to make the buffer? Okay, and so the Ka here of our bicarbonate is 4.7 times 10 to the negative 11. So in this pair, this HCO3 minus is our acid, and CO3 2 minus is our base. So we're given pH is 10, and our system is our bicarbonate is going to be our acid. Whoops, got too used to drawing that from the last problem. Bicarbonate is our acid. It's going to produce carbonate and H3O plus. Okay, so that's our equilibrium. We're given a Ka value equals 4.7 times 10 to the minus 11. We're given our volume is 1.5 liters. Okay, and then our initial concentration of our HCO3 minus bicarbonate is 0.2 molar. Okay, so this is what we're given to start with. Okay, and it's a buffering system, so you can probably bet that you're going to have to use the Henderson-Hasselbalch equation. And remember, that's log of base, which in this case is carbonate, over acid, which is bicarbonate. Well, you can see we need a pKa value for this equation, and we're given a Ka value. So to convert pKa is going to be the negative log of Ka. So that is negative log of 4.7 times 10 to the minus 11. So that will be 10.33. Okay, so that's our pKa. And we have our acid concentration, and we have a pH that we want, pH 10. That's our target pH. So now we have to rearrange this to solve for the concentration of our conjugate base that we would need to add to this system to a solution of our weak acid to give us a desired pH. Right, so to do that, the first step, if we subtract pKa from both sides, So then we'd have to take care of that log. So we would raise 10 to the pH minus pKa equals base over acid. Then we'd multiply both sides by the concentration of acid. So we get 10 to the pH minus pKa times the concentration of acid. That's just minus, equals our base concentration. So we can plug all those values in. So 10 to the, 10 minus 10.33 multiplied by 0.2, and that's going to be 0.094 molar. Okay, so that's the concentration we need to add, or we would need to have of that conjugate base to give us a desired pH. But we're adding this as a solid to a certain volume of our weak acid solution, right? We have 1.5 molar of that solution. So how much would we need to add in mass? So for that, you would take your concentration that you need, 0.094 moles per liter. You multiply that by the volume, which is 1.5 liters. That gives you 0.141 moles. Right, and then you would take that number of moles you need, multiply that by your molecular weight of your CO3. So if I calculated that right, it should be about 60 grams per mole for CO3 2-. So this gives us 8.46 grams of base that we'd have to add to our solution to get that desired pH. So lastly, we'll talk about acid-base titrations, and we'll pick this up again next time to finish it off, but just an introduction. An acid-base titration, the concentration of an acid or base is determined by neutralizing the acid or base with a solution of the opposite base or acid that you know the concentration of. Right? Equivalence point, that's when the reaction occurs where you have the same number of moles of, if you're adding a base, you add the same amount of base to the number of moles of acid that you originally have, or vice versa. The end point is when the indicator changes color, so hopefully your indicator endpoint will be the same point as the equivalence point. And so we've probably all done this in lab enough, but in this picture here, we have a solution of HCl and we're adding NaOH to it. So you're adding NaOH here to your solution of HCl, and as you add that NaOH, the pH doesn't change very much at first, right? Because you have a very acidic solution, you have more H3O plus involved. But as you're adding that base, that OH, is going to react with the H+, and eventually you're going to reach a point here at pH 7 where you've added the same amount of moles of base that you have of acid, and you'll reach the equivalence point. Okay, so the pH goes up very, very high at that equivalence, like near that equivalence point. And then as you're adding more base than acid, you overshoot it, and your pH gets very high and starts to plateau out. So if you want to calculate the pH during a strong acid, strong base titration, what do? Well, you know the initial pH is going to be equal to your acid, the initial acid concentration. Your pH, therefore, is just going to be negative log of your initial acid concentration. The initial moles of your acid is just going to be the volume of your acid times the concentration, molarity of your acid. So the moles of your base added has to equal the volume of the base times the molarity, the concentration of your base. And so at any point before the equivalence point, the moles of your acid remaining would just be the moles of your acid initially minus the moles of your base added. Okay? So then that H3O plus concentration at any point is going to be moles of acid remaining divided by the volume of your acid plus the volume of the base that you've added. Okay. And again, you calculate, after calculating that concentration, you can calculate the pH at any point. pH at the equivalence point for a strong acid, strong base titration will be 7. Okay, a pH beyond the equivalence point, how you would calculate that, you would need to know your initial moles of your acid. Again, that's the volume of your acid times its concentration. The moles of OH added, which would be the volume of base times the concentration of base. And then you'd find the moles of excess of base that you've added now, right? Because you're after the equivalence point, you've already added more base than you have acid. So you have to take into account how much excess base you have. So that'd be the amount that you've added, the moles that you've added of base, minus the moles that you started with of acid. Okay. To find that concentration, then, it's the moles of excess divided by the volume of acid plus the volume of base that you've added. And then once you get that, you would calculate a POH, taking the negative log of that, and then you convert to pH using that pKw. So an example of this, a strong acid, strong base, if we had 40 milliliters of 0.1 molar HCl titrated with 0.1 molar of NaOH, the initial pH is simply the pH of this HCl solution, right? So our initial concentration is 0.1 molar, so we'd take that's a strong acid, so it's completely dissociated, so that would be the same concentration as our H+. So we take the negative log of that, so our pH would be 1. Okay. Now if we want to calculate the pH after 20 mils of sodium hydroxide has been added, how do we do that? Well, we need to know how much of that acid has reacted with the base that's been added. So the initial moles of H3O plus would be 40 milliliters, 0.04 liters, times our initial concentration, which would be 4 times 10 to the minus 3 moles. Okay, we've added amount of base, 20 milliliters, 0.02 liters, times 0.1 moles per liter, same concentration. Our base has the same concentration as our acid. So that is 2 times 10 to the minus 3 moles. Okay, so the OH ions are going to react with an equal amount of H3O plus ions from our acid. So the amount of acid we have remaining would be the amount we started with, 4.0 times 10 to the minus 3 moles, minus the amount of base we've added, which is 2 times 10 to the minus 3 moles. So we'd be left with half, essentially, 2 times 10 to the minus 3 moles. Then we could use that to calculate a concentration, right? So that's our number of moles. Our concentration now, we started with 40 milliliters, but now we have to take into account we've added 20 milliliters from our solution of base. So now our concentration is going to be moles per total volume, which would be 0.033 molar. We could use that to calculate a pH, which would be 1.48. Okay, so the equivalence point occurs when the moles of OH added equals the moles of HCl. So for that, we'd have to do it at 40 milliliters of NaOH being added. And so OH, if we had 0.05 liters, 50 milliliters, this would be a case where we have an excess amount, right? Because the equivalence point would be at 40 milliliters. So if we had 50 milliliters of base, that'd be 5 times 10 to the minus 3 moles of OH. So we would just subtract the starting amount of acid that we had from that to get the excess amount of moles of OH that we've added. And we could then use that to find a concentration of OH. So we have 1 times 10 to the minus 3 moles excess, and the total volume would be 40 milliliters of acid plus 50 milliliters of base that we've added. So 90 milliliters or 0.09 liters. And the final concentration of OH there would be 0.01111. Take the negative log of that to get POH, and then subtract it from 14 to convert it to a pH. Right, so that's how you would calculate the pH at any point in a titration of a strong acid and a strong base. Next time we'll pick it up and talk about the more complicated situations of weak acid, weak base titrations.